Okay, so it looks like recording started. Cool. Yeah. So I had just briefly signed on, and I wanted to say hello to everybody, and sort of I don't want to steal Nichelle's thunder with my intro, my real intro, but I was simply saying that I'm a BME PhD student, and I became a grad student before the imaging sciences program it really existed, and the program kind of lived more informally in the BME and the ESE departments, but it's kind of cool that it's its own program now because it really is a separate field. And in terms of my background, I look a lot like an imaging sciences PhD student because I've taken a lot of the courses that go into imaging science, and that's where my interest is and that's where my research is. But I came around prior to imaging sciences having its own formal home. So I'm technically a BME student, but it's nice to have new people in the imaging sciences program and basically just welcome. So how has the course been going so far? Like I've not been to any of the sessions. This is my first one. Has it been like pretty well attended? Roughly, like how many people have been coming every week, and how do you think it's been going?
Welcome to your first course, to your first part of the math crash course. You know, I mean, we set it up to have people drop in as they can and as is like useful for them, right? So like attendance is slightly outside of the course goal, but we have like a few regulars who come to most problem sessions, if not all of them. With most of the people who come to all of them. I think we have like 3 or 4 in the early sessions and like 1 or 2 in the later, depending. But seems like we maybe have a few more people than that who, I mean, 1 are here. Hello, welcome, thank you for coming. And also, you know, like can't make the problem sessions or prefer to just like engage with the stuff on their own time and whatever. But so, you know, I 6 folks who I see every week, but maybe more outside of that.
Yeah, I saw when I was prepping this, I was taking a look at the course outline for linear algebra to see like what, you know, what's been covered, what I should assume people know and don't know yet. Mm-hmm. And I was like, it looked like basically a very solid like selection of like the super important material from like Math 309 here, which is like junior level matrix algebra, sophomore junior matrix algebra here, which is like normally what you would want like a graduate engineering student to come in with. So it's like, I think the folks who planned the course did a very good job of serving its purpose, its intended purpose. So hopefully, and my talk will actually get into, because it relies on some of the material in the elective modules, but I did not assume that people coming to this talk would know everything in the elective modules. So I will be giving like a brief like overview of some of that stuff anyway, which will then hopefully maybe be even a better foundation for them to pursue those elective modules on their own and be like super ultra prepared for sheer math of imaging sciences, which I guess probably starts out with a singular value decomposition and just like rips from there. So anyway, well, yeah, I won't like ramble too much. If you feel like we have a full crowd, then I don't want to delay, but I also wanted to give, you know, people some time to filter in and give my PowerPoint a chance to upload to Box, my own private Box folder, just so that in the event that for some reason, like my computer crashes, I don't have to like show you an empty PowerPoint or turn this into a whiteboard talk. Maybe I should have paper here. I don't have paper, so if I have to draw, I'll be typing in LaTeX, or maybe not LaTeX, PowerPoint. I'm happy to do like whiteboard style stuff, but yeah, I maybe should have had like a piece of paper here. I think I have a piece of paper over there, but it strikes me as something that might have like a social security number on it, so I probably shouldn't use that as scratch paper.
Yeah, maybe don't. Honestly, it's recorded.
We probably could have sent you one of our iPads that we got for the summer program specifically, just to do like whiteboard stuff.
Oh my gosh, that's so fancy. That's so fancy. But that would rely on, well, I will not be mentioning how much I actually physically come into the lab these days. That might be a little bit. That might be.
No worry, we do home deliveries too. So,
oh, neat. Okay, cool.
Yeah.
Well, you at least know that I came in yesterday because I was doing MRI stuff. I do come in like usually every week. Just, I mean, I had COVID before, so like, and then was in Scotland, so I've been pretty disconnected from the physical part of the lab. But lots of Zoom. So anyway, okay, cool. Well, I'll let you run. I'll let you run things. I don't want to like commandeer everything until it's time. So thank you for letting me
I think, yeah, we can go ahead and get started. And then if people filter in, we'll be recording this. So if anyone wants to see the full thing, they can always like look at the recording later. And I know some people want to, but they couldn't specifically make this time period. So Zach already said, wonderful intro. He's a PhD candidate in biomedical engineering at WashU. He also did his undergraduate degree here in physics and math. And he's actually been in the research lab for a while. I actually knew him from my research assistant days before I started the imaging science PhD program. So currently he works in Dr. Joe Culver's Biophotonics Research Center, formerly known as the ORL. And he also works with Dr. Mark Anastasio, which some of us will know that he was at WashU previously. Currently he's at the University of Illinois at Urbana-Champaign. So his research, Zach's research interests are in neuroimaging system design, computational image reconstruction methods, neural decoding, and neurological and psychiatric disorders. And his dissertation focuses on developing diffuse optical brain imaging systems with high resolution and decoding information about what the subject is seeing, hearing, or doing based on their image brain function. And one application of his work is to improve brain-computer interfaces that expand severely paralyzed patients' communications. And today he's been really kind to give a talk about linear algebra and diffuse optical tomography system design, image reconstruction, and regression modeling. So Zach, I'll let you take it away.
Sure. Okay, I am going to go ahead and share my screen. And I'm going to go ahead and let me know if this looks like a sane view of my slides.
It looks
This looks good.
Great.
Yeah,
perfect. Okay, so that was a great introduction. Thank you so much, Michelle. It's very kind. Obviously the intended audience of this talk is folks who are taking this summer boot camp in linear algebra, and so this talk is kind of the end of the linear algebra unit, and it's designed to give you a taste of some of the things that we use linear algebra for, or at least that I use linear algebra for. So this talk will have a fair amount of information about diffuse optical tomography in it and the applications, but there will be, especially the middle section, there will be a lot of just foundational linear algebra math and the connections between those topics. So if you're just here for the DOT, you will still get new information, but it will be mostly at the beginning and mostly at the end of the talk. And I should just add that a lot of, not all, but some of the slides were taken from these couple of conference talks that I gave, just so that I can properly credit the people who helped me do that work. So this talk, primarily the end goal is going to be about neural decoding. So I first want to explain what that is. So neural decoding in this context is that when a subject is presented with or imagines a stimulus, that stimulus evokes brain activity, and neural encoding is the translation of those stimuli into brain activity. Neural decoding goes in the opposite direction. So in decoding, we infer partial information about the stimulus from measurements of brain activity. And some examples of neural decoding in literature include the following. So a simple example would be during some optical brain imaging with FNIRS, subjects might imagine flexing their left hand or their right hand or doing simple math in their head. And then the imaging data would be used to guess which action they were imagining at a particular time point. A more advanced case of this would be during MRI to show subjects 1,750 images, build a model that predicts their brain activity that gets induced by the visual features of the images, and then show 120 new images and use that model to guess which of the images the subject was viewing at each time. So that study was done by Jack Gallant's lab in 2008. And more recently, folks have used implanted electrodes, specifically ECOG or electrocorticography electrodes, in which subjects read a bunch of sentences, and the scientists built a model that predicted speech-related movements and sounds in their like head and throat area from the electrode recordings. And then they had subjects voicelessly mouth new sentences and used their model to synthesize audible versions of those sentences from the electrode recordings. So you silently speak a sentence, you move your lips, but you don't use your voice, and they like they reconstruct what sentence you would have said if you could talk. Let me go ahead and, oh yeah, Michelle, thank you for reminding people that they're welcome to interrupt if they have questions. So one of the most prominent and clinically significant applications of neural decoding is brain-computer interface. So for patients with severe movement impairments, restoring even just like a small amount of communication and control can superbly improve their quality of life. So as an example, if you could allow a patient with locked-in syndrome, so complete paralysis, to just say the word yes, no, or I'm in pain, in a coded way by imagining their left hand flex, tapping their tongue, or doing mental math. Or in a more advanced case, you might have their imagined actions control a cursor on the screen so that they could spell words with a keyboard. And that latter type of thing was done with an implanted array of electrodes in a 2007 study by Chidan Pandaranath et al. And on quadriplegic patients, one of whom is shown in this photo using an on-screen speller. So this is a huge game changer for people who are paralyzed, as you might imagine, if and when it works. As you might imagine, there are challenges with this technology. So one of the biggest trade-offs is this trade-off between the decoding performance and the invasiveness that's available or that's present among current available technologies. So non-invasive techniques such as EEG and FNIRS, which you can wear and you don't have to cut your skull open for, have lower decoding accuracy and have not been able to decode as many items or as fine-grained of information as techniques that do require surgery, such as ECOG and intracortical electrodes. The second major challenge is that there's a trade-off between that decoding performance and the bulkiness and cost of the systems. So fully wearable and portable technologies like EEG and FNIRS also have lower decoding capabilities than functional MRI, which requires a large fixed magnet that costs on the order of $1 million. And so the key point here is that high density diffuse optical tomography, which is abbreviated HDDOT, has the potential to fill a void among the current technologies for the following reasons. First of all, it has a spatial resolution that's intermediate between FNIRS and fMRI, which should give it a decoding performance between FNIRS and fMRI. And right now, it also has portability that's between FNIRS and fMRI. The systems are still kind of bulky, but there are wearable versions emerging. And I cited some papers and conference presentations there, so you can check out some of the cutting edge systems that are being developed, one of which, this Agato et al. Agato is Alvin Agato, who is actually one of your classmates in the PhD program for imaging sciences. He and a couple other people are leading the charge to build such a wearable system in our lab. So the goal of the current study is to evaluate feasibility and performance of decoding the identities of some movie clips that human subjects viewed, and to decode that information using DOT. So, okay, so what is diffuse optical tomography? So DOT is basically an alternative to functional MRI in certain situations. So functional MRI images blood oxygen fluctuations that are related to brain activity. DOT can serve as an alternative to fMRI in situations where fMRI is not possible, such as the intensive care unit or in lower resource settings where they can't afford a big scanner. DOT images similar blood oxygen signals as fMRI by shining near infrared light into the head and measuring the amount of light that scatters back out. And this works because fluctuations in the blood oxygen level in tissue between and beneath a source and a detector of tissue cause fluctuations in the tissue's light absorption and the measured amount of light. And by placing many sources and detectors on the head, we can localize the light absorption changes and reconstruct images of those absorbance fluctuations. We use 2 wavelengths or colors of light to separately image the concentration fluctuations in oxygenated and deoxygenated forms of hemoglobin. And that works like a pulse oximeter, essentially because when blood is more oxygenated, it's redder. And when it's not as oxygenated, it's more purple. But because near infrared light scatters a whole bunch in biological tissue and doesn't penetrate super deep into your head, like it only goes about 1 to 2 centimeters deep, this DOT technique is lower resolution than fMRI, and it can only image near the brain surface, which is called the cortex in biologist terms. If you shine near infrared light into someone's head and it comes out the other side, that person has some issues and should probably see a doctor. So that's where some of those limitations come from. So let me check. I think I might have a question. Yeah, so there's a great question about why the light path could be curved. And the answer here is basically that there are so many times that a light particle scatters in the tissue that it scatter by the time it gets down to about here, about 1 centimeter deep, it has scattered so many times that it could be traveling in any direction. And the reason why I'm showing a curved light path here is that for this particular source and detector, for the detector to see the light that comes from this source, it's only seeing the fraction of the light that goes through this curved path. You could also put a detector here, and in DOT, we put sources and detectors all over the head. And so there we can see the light that travels through different parts of the tissue. And that's why, so really the light path is all over the place, but the light that we measure has taken these kind of curved banana-shaped paths. Does that make sense? So, okay, so this is an example of the image quality of HD-DOT. So subjects here viewed this flickering checkerboard wedge that rotated around the screen. And basically, because of the way the visual cortex is organized, as a stimulus moves around in the visual field, the activation, the place of the brain that lights up, also moves around that back area of the brain in a continuous manner. That property of the brain is called retinotopic organization. And it can be used to validate an imaging system because we kind of know what the activity should look like in response to a stimulus like this. So here, what you can see is that there's a pretty good correspondence between the HD-DOT images and the fMRI images, but the HD-DOT images are blurrier. The HD-DOT resolution is about 15 millimeters from a high density system. It's higher for an ultra high density, which I'll talk about a little later. And the localization accuracy is that there's usually an error in positioning of about 5 millimeters, which is actually pretty good. There are also you don't just get similarities in a visual task, you get them in these various language tasks that are shown here, like hearing words, reading words, and imagining speaking words. So on the middle panel here, you can see the activation pattern that comes from the HD-DOT system. And on the right, you see a comparison to the same the same tasks performed by the subjects in an fMRI scanner. So the goals of this study are to evaluate feasibility of decoding which of several movie clips was viewed using HD-DOT, and to also evaluate whether if we double the density of our source and detector grid, so if we use a lot more sources and detectors placed super close together compared to the current standard, which we're calling high density DOT, this new one would be ultra high density. Do we get something out of like blasting up our capacity of sources and detectors? Do we get better decoding performance? Can we better distinguish which movie clips were viewed, which could then be used to more accurately tell like what a subject would be doing or imagining in a later study? So the spoiler alert is that image quality, just baseline image quality, does improve by further decreasing the optode distance. So way back in the day, like 10 to 20 years ago, people did a lot of experiments with something called a sparse nears array, which had sources and detectors arranged in about this density on the head. And people still use these systems because they're super lightweight and portable and they're cheaper. But our lab kind of made these higher density systems which give you better resolution than these sparser imaging systems. And so, you know, one question is, if we make it denser, do we get an improvement? The spoiler alert is that we did find that the answer is yes. I'll talk about in great detail how we showed that and why we thought that was a good idea, like why we didn't think we'd hit a ceiling. So imaging systems are expensive to build, and before you build one, you generally want to do some simulations to see if your hypotheses and designs of the imaging system are correct. So I told you that increasing the opto density of the grid improved image quality, and that was a finding that initially got found in simulation. So what you can do is just on a computer, you can pretend that you have a blob of tissue and you stick a fake activation, which is called a point target, in that tissue. And then you can simulate the measurements that you would get from a DOT system that has sources and detectors at different spots on the head like this. And then you can use an algorithm to reconstruct an image of the point target that you simulated the measurements of in the tissue. And in an ideal, a perfect imaging system would just give you a picture that looks exactly like the fake point target. But imaging systems are not perfect. They throw away information and they blur things. So you get instead these pictures that don't look like single points. They look like blurry and funny shaped points. And this picture is called a point spread function. And here, what you can see is that from the high density grid, you get a point spread function that is narrower and also is at least symmetric and nicely shaped around where the initial target was. Whereas if you use these sparser grids, you get this super wacky shaped point spread function that's also broader. So there's more localization error and resolution or in lower resolution from these sparse grids, even just from simulation. You can imagine that that even gets worse in experiments, because in experiments you have noise that's usually worse than your simulated noise. So we did the same kind of study with an ultra high density grid. We simulated a fake activation, which is shown in this movie as like a little green dot in the brain. And the reconstructed image that you get from that is the heat map around it. And on the left side here, you see the images that we got for each of the reason the dot's moving is that like each position of the dot corresponded to a different place where we put the one point target. And you can see that the ultra high density system gets closer to the correct depth and also has a slightly narrower point spread function than the high density system. And obviously we want to be quantitative about this. We don't just want to look at pictures and make claims based on artistic impressions. And so even though that can be a great starting point, so this shows the width of the point. On the left panel, you see the width of the point as a function of the depth that the green target was at. And in the black line, you see the performance, the resolution that we got from the high density system, and the red line is from the ultra high density system. So you can see there's about a 20 to 30%, and in some cases, even a 2 times improvement at shallower depths in the resolution from this. You can also calculate how far off it was from that green point. And because you can take repeated measurements of this image over different instances of noise, you can get a sense of the signal to noise ratio as well. You can see that the red, the ultra high density system gives us higher signal to noise ratio than the HD system as well. So the linear algebra part of this comes in how we did this study and how we understood why the results turned out they did. And they also kind of teach us why the study worked in the first place. So to talk about this, I can tell you that it turns out that in DOT, there's a pretty good model of the imaging system is this one. And it is a linear forward model because it says that the stuff that you measure, the measurements can all be arranged into a vector y, where each element of y is basically the log ratio of the light intensity that you measure divided over, so this is at a given time point, and it's divided by the mean light level that you get in a detector for a given source over time. And this log ratio, I can show you in a different slide if you want. This is a kind of a funny way of measuring the percent change. So if you had a baseline level phi 0 and it fluctuated around that baseline, this is roughly calculating the percent change. but it does so in a ratio metric manner instead of subtractive, because subtraction takes away significant figures when you're subtracting out like a big number from another big number. And it also lines up better with the physics to calculate this funny version of percent difference. But I'm not going to dwell on that because it's not really linear algebra. So basically what this says is that the stuff that you measure is some weighted combination of the brain activity, which is really a fluctuation in the amount of light that's absorbed at a particular spot in the brain. And this sensitivity matrix is dictated by the physics. So that sensitivity matrix has dimensions because X is a vector that tells you how much activity there was at every spot in the brain. There are n voxels and there are m measurement channels. And so the matrix that relates them has dimensions m by n. And you can see here that if you take a row of that matrix, because the rows of the matrix have the same number of elements as X, you can plot the rows of the matrix at each voxel they correspond to get the sensitivity profile of that measurement in that row. So here is a heat map of the sensitivity profile, which basically shows you that it shows you which voxels this measurement, you know, when I say measurement, I mean the light that gets measured in this detector from this source. The hot spots are the part of the brain that this measurement is particularly sensitive to. So the weights here, the A elements are super high for these red levels, and they're super low when you get further away from the source and the detector. And that tells you that if there's an activation super deep in the brain, it's going to get multiplied by a bunch of elements of A that are 0, whereas if it's close to the surface, it's going to get multiplied by big elements of A. And so those are going to be like increase the sensitivity of your measurement Y1 to the stuff that's happening at the surface of the brain. So this is great. We measure Y. We use the physics to get A. E is some noise that I'll talk about how to handle a little bit later. But basically, this is cool because you just spent a whole bunch of time in linear algebra figuring out how to solve equations that look like Y equals AX. We want to find X. We know Y and we know A. And so linear algebra, it turns out, helps us a lot with this. And so, so that we can use linear algebra tools, we're going to start off with attempting to solve Y equals AX for X. That is a reasonable starting point because on average, these noise vectors look like wiggles around 0. So on average, each element of E will be 0 over repeated measurements. But I will talk a little bit on how we handle E later. For now, though, I want us to start with just the simplest case, which is solving Y equals AX in this context. So again, you guys spent a whole lot of time on Y equals AX this summer. So question number 1, can we simply calculate X equals A inverse times Y? The answer is no. Why not? Well, first of all, A is almost never square in practice. So for example, usually in medical imaging, we have a lot fewer measurement channels than voxels. So that corresponds to an underdetermined problem where you have fewer rows than columns, also known as fewer equations than unknowns, or no, sorry, more unknowns than equations. Yes, that's just another way of saying the same thing. And yes, A does depend on the structure of the brain. But what we do is we actually start, so the job of DOT is not to image the structure of the brain, it's to image the activity in the brain. So what we will usually do in DOT is we will take like an MRI of someone's head or an atlas head, like if we don't want to give them MRI, we'll take like another subject's MRI or an atlas, and then we'll register that person's like brain or head shape to that atlas. And then we will make a light model, assuming that that's their underlying anatomy. And then the job of DOT is to determine what brain function is superimposed on that anatomy. Does that make sense? Yeah. Yeah, it's a little bit funny because DOT is a functional imaging modality and not an anatomy. You can use DOT in some situations for like anatomy when your anatomy corresponds to absorption parameters, but it's more rare to see DOT in that context. Even in breast imaging, for example, like you're usually looking for like parts of the breast that would light up in a tumor, like if you gave a contrast agent that would then get absorbed more by the tumor. So even like breast DOT can also usually be like, I think it's usually functional DOT. I don't know, maybe if a breast imager were here, they would tell me that I'm wrong. And if you know that, then tell me if I'm wrong, because I'm now being recorded maybe saying wrong stuff, which I don't want.
I only know breast imaging in the MRI context, but I don't think you're wrong.
Okay, cool. That's good to know. Okay, cool. So let's jump in with y equals ax. So a is almost never square. And now you're going to say, hey, wait a minute now. But if it is an underdetermined system, then doesn't y equals ax have infinitely many solutions, because you can come up with a bunch of x's that give you the same y, and y must have come from ax due to the physics, right? Well, not quite. The reason is that the model y equals ax isn't perfect, and computers can't store all numbers with infinite precision, even if there wasn't any random noise like in your electronics. And then when you include random noise, you make matters even worse. So then the mismatch between the model and reality gets worse, and you can't necessarily trust that y is going to be in this column span of a. It may not be expressible as a linear combination of a's columns. So, okay, but what about if the columns of A span all of Rm? Well, in that case, y has got to be writable as ax, right? Because y is inside Rm, and everything in Rm can be written as a linear combination of things in A. Well, okay, unfortunately for us, we have another problem here, which is that typically the columns of A are almost or completely linearly dependent. So they almost or completely don't span all of Rm. What does almost mean in this context? I'm glad you asked. I'm about to get to that. So roughly speaking, this is because the sensitivity profiles of a real imaging system have blurring. You notice that those like banana-shaped functions that I showed you were really blurry. And it turns out that for nearby measurements, they blur together a lot. And those blurrings cause rows and columns of A to be nearly parallel, or more generally to be linear combinations of other columns. And another way to describe this property is to say that A is ill-conditioned. You'll hear that term a lot. So what on earth do I mean by almost linearly dependent? Because when you say almost linearly dependent, like a mathematician might shoot you. So like, this is what I mean by almost linearly dependent. So here are two vectors, which might be columns of A. What you can see is that they're almost parallel. So you know that two vectors that are parallel, like if you have them and they're parallel, they automatically make the set that they're in, they contaminate it. They make it linearly dependent. So these are almost parallel. And the reason why this is still a bad thing for us is that this makes X super, super sensitive to Y when you're trying to solve Y equals AX for X. And the reason for that is that if you get a Y vector that has any component that is along the part of these vectors that isn't really particularly big, you have to add a huge amount of the vector A2. In other words, X2 is going to have to increase a lot in order to like account for and explain this purple vertical component of Y. So if you change Y a little bit, it's going to massively change X2, and that does what we call destabilize your solution. So even if your vectors are technically, they span all of Rm, it might be that the way in which they span it is like super bad and makes it sensitive to noise. So, okay, great. So now you probably believe me that we can't use all the tricks that necessarily you've learned up to this point. I don't know if least squares has been covered. I think that was an optional module, so I'm not assuming that. So congratulations, I'm going to be covering some of that here. So we're going to use this technique called ordinary least squares estimation as a first draft way to get around these problems. So we can't exactly solve Y equals AX in a stable manner. So we're going to do the next best thing, which is we're going to just find the X that minimizes the mismatch or distance between the vector Y and the vector AX. We're going to call that minimizing vector X hat. And this is called the ordinary least squares estimate of X. Why is it called that? Because when you minimize that squared distance, you are minimizing. So last time I think you covered vector length, and you might remember that to calculate the length of a vector, you square all of its elements, you add up the squares, and then you take the square root of it. So the square of the length is just what you get before you take the square root there. So minimizing distance squared is equivalent to minimizing distance itself, because the square is a strictly increasing function, and other reasons that I don't want to be precise about stating so that I don't trip over myself verbally. But basically, we're trying to minimize this distance between y and ax, and we're going to try to pick the x that minimizes that distance, the squared distance here. And ax has to be in the span of the columns of A, because ax is literally a linear combination of A's columns weighted by the components of x. So I want to remind folks that this is just a triangle illustrating what vector subtraction looks like. So if you have a vector y and you have a vector ax, and you want to look at what y minus ax is related to y and ax geometrically, you can see that if you arrange y and ax with the same tails, the first vector and the second vector, the one after the minus sign, the difference vector connects the two, and it goes from the head of the negative vector to the head of the first or positive vector in that difference. So you might imagine that if we want to make y minus ax as small as it can be while making sure that ax stays in the span of A's columns, y minus ax is going to turn out to have to be perpendicular or orthogonal to the ax that comes out of this. And there's a neat proof by contradiction, if you want to see it, that involves drawing a sphere and showing that if the sphere touches this plane in two places, then you can always make a sphere that's smaller. So if you draw a sphere around y, which represents distance from y, that distance is going to be minimal when the sphere is tangent to this plane and not intersecting the plane in two places or more. But what I want to be clear about is that this y minus ax hat is called the residual vector. And I'm showing here this plane. This is an example in 3 dimensions. And here, A1 and A2 might be the columns of A. This is actually an over determined case, because this would be a 3x2 system, but no matter. I mean, the concept is the same. The idea here is that the distance between ax hat and y, or ax and y, is going to be minimized when this is orthogonal. And so this picture, this orange, red, and pink triangle here is actually a right triangle, where this right here around this ax hat point is a right angle. So that's cool. We know that geometrically what we're looking for now, but we need a formula, right? We need to ultimately be able to calculate what that is. And so in order to do that, I am going to lean on calculus. And the reason is that this y minus ax squared thingy that we're trying to minimize is a differentiable function of the components of x. So to find what might be a minimum or a maximum or a saddle point, so a stationary point of this, I'm going to set the gradient of f equal to 0 to identify where this might have minima. And so here we go. If you want to see how to do this, really, when you take these derivatives, you have to do them in scalar form, but there's a cool way to arrange them in vector form. So I'm using some of those shortcuts here, but this is really just so that I don't have to spend the whole lecture taking derivatives. But I'd be more than happy to show you like the process of taking each of these partial derivatives and then arranging them into a vector. But the end result of that is that the gradient of f equals 2 times a dagger. This is the conjugate transpose. So if a were complex, this dagger just means that you transpose a, but you also take the complex conjugate of the stuff in a. For this talk, everything in a is real. So like I could give this talk with just transposes, but I'm giving you daggers so that I can give you the most general results possible, so that if one of you works with an imaging modality that does have complex numbers in the forward model, you don't like get totally thrown off by the fact that you have daggers and you don't do things like forget to take the complex conjugate when you should be. So okay, we set this equal to 0. It turns out that that happens when a dagger a times x equals a dagger y. And you can solve this by saying x hat equals a dagger a parentheses inverse times a dagger y. And a reminder here is that the inner product between two vectors, which is also called the dot product, is that you take the first one, you conjugate transpose it, and then you multiply it by the second one. And that has the following notations. Everybody here has covered dot product, right? Perfect. Okay. So a hash is called the Moore-Penrose pseudo-inverse of A. It has the size n by n. A dagger A is a square matrix, n by n, and I just assumed something. I just assumed that a dagger A is invertible. It's at least square, and it turns out that it's not always true that a dagger A is invertible. It's usually close. But let's assume that it's invertible for now, and then I'll talk about how to handle that generalization later. For those of you who know something about a dagger A already, the reason why a dagger A might be invertible is that the columns of A would be linearly independent technically, even though they're close to linearly dependent. The columns of a dagger A are also usually close to linearly dependent, but they might still span all of Rn. But there is a way to handle when this isn't invertible that I'll talk about and ultimately use. So ride with me for now, and then I'll show you how we can adjust the problem just a little bit to account for that case. Okay, so we found a stationary point, right? You set the derivatives equal to 0, but that's not enough, right? Because a stationary point can also be a saddle point or a maximum. And so how do we know it's a minimum? Well, we check the second derivatives. It turns out that it's convenient to arrange those second derivatives into a matrix H, which is also called the Hessian matrix. H is square and symmetric. Okay, why is the second derivatives a matrix? Why do they form a matrix and not just a vector? And the reason is that when you have multivariable calculus, right, you're not just taking like the derivative with respect to x1 twice and the derivative of with respect to x2 twice. You also have to deal with the mixed partial derivatives like d by dx1 dx2 and d squared by dx2 dx1. You might also remember, hopefully, that the mixed partials don't care about what order you take them in. And so that's why H is symmetric. Because if you take the derivative with respect to x1 and then x2, and then you do it in the opposite order, you're going to get the same mixed partial second derivative. So, so this Hessian matrix, of course, that means that we differentiate the gradient in all the ways we can. And it turns out that for this function, the Hessian matrix is 2 times a dagger A. That is cool because there's no x in here. So that means that H is actually the same everywhere for all values of X. And how does this let us tell if we have a minimum, right? So if you remember from like Calc 1, if your second derivative is positive everywhere, your function is convex, and that means that you've got a minimum. But in multivariate, there's an analogous way of analyzing things. And so to see that, I'm showing you the Taylor expansion of F about X hat, which is an approximate way to calculate what F would be if you started at X hat and you took just a tiny step away, which we call delta X. And so that Taylor expansion says that you start with F of X, and then you take the dot product of your step with the gradient of Fx. And then you also have this second order term, which involves all of the different second derivatives. And again, I'm just for compactness writing this in vector form. And then after that, you have more stuff in your Taylor expansion that is super small because it has it's on the order of the length cubed and the step is small. However, when you're near a stationary point, we just said the gradient was 0. So this term here goes away. So if you want to find out how much you're changing, you can't just use the first order term. You actually have to look at the second order term. because otherwise you're just going to look at F and you're going to say the function doesn't change and you're going to throw away the baby with the bathwater. Okay, F will always go up if this red thingy here is always positive. So it turns out that F will always go up if for any step W or delta X that you pick, this thing is bigger than 0. That property is also called positive definiteness, and it is equivalent to all of the eigenvalues of H being positive, greater than 0. So to see that, I'm going to write out what would happen if we took a vector W and we took its dot product with the vector HW. So if you do that, then H, remember, is 2A dagger A. This is what we get from that. We get W dagger times A dagger A times W. And this can actually be rewritten as the inner product of AW with itself, which is another way of writing the squared length of AW. And I did it. This is a boo-boo on it. This should have a 2 here. You see, some of you may have caught that. Yeah. I missed a 2. Hello. Let's see if it will let me go back. Good. So this, because it's a length squared, it's always going to be at least 0 because lengths are not negative, but there's an equal to here. So if W, so I just said that W, you have to pick a step that's not 0, otherwise it doesn't count. So even if W isn't 0 though, remember that AW could still be 0 if the columns of A are linearly dependent, right? So this would mean that A has a non-zero null space. And in that case, AW might be the 0 vector, even if W is not the 0 vector. So all we can say from this is that H isn't quite positive definite. It's called positive semi-definite, which means that it's almost positive definite, except there's a less than or equal to sign here instead of strictly greater than 0. Positive semi-definite is the same thing, is equivalent to all of the eigenvalues of H being non-negative. So positive definite means all the eigenvalues have to be greater than 0. This just means they've got to be greater than or equal to 0. So this is a very special matrix, this A dagger A, and I'm going to talk about it a little bit more because it lets us get some more insight into A itself. So A dagger A, if you take the eigenvalue decomposition of it, you get a very special thing called the singular value decomposition. So it turns out that you can write any matrix A in this way, U, S, V dagger, where U and V contain orthonormal bases for the image space X and the measurement space Y. Just like how if you had, a square matrix, right? If you take the eigenvalue decomposition, you could get a bunch of eigenvectors, right? And those eigenvectors form the basis for the column space of that matrix, the span of the matrix. Here, you're just taking the eigenvalue decomposition of A dagger A. So if A dagger A, remember the eigenvalue equation, which says that your matrix times an eigenvector V equals a number called the eigenvalue times that eigenvector. So this equation, A dagger AVX equals S squared K times VK, is one of the eigenvectors and eigenvalues equations for A dagger A. Okay, now you notice that I put a squared here. So you all might be sitting here and thinking, you're silly. How do you know that the eigenvalue is going to be positive? And moreover, how do you even know that it's going to be real? So it turns out that there's a special property of this kind of matrix. Anytime you have a matrix that is called Hermitian, which means that it is symmetric, well, what it means is that A dagger and A, or rather that the matrix, if you take its conjugate transpose, gives you the same matrix back. So if it's real, it just means the matrix is symmetric. A real symmetric matrix is Hermitian. And it has that kind of matrix, which A dagger A is, because if you take the transpose of A dagger A, you get back A dagger A. Then you know that the eigenvalues are going to be positive and real. And you also know that there is going to be a basis of eigenvectors that is orthogonal. That's very cool. It's very helpful. It's used all over the place in physics. And so because of that very special property of symmetric or more generally symmetric real or more generally Hermitian matrices, that's why I can write down this equation and I know that these eigenvalues here are positive. So you can take the square root of them to just get S's. And when you do that, you can write out this A as this sum of the eigenvectors U's and V's transpose or conjugate transposed. What are the V's? Well, or what are the U's here? Well, here it's kind of cool that you can show that you can calculate the U's from the V's, because this equation here, if you just take it and you multiply it on the left by A, then you actually get another equation that looks like an eigenvector equation, where the eigenvector is AV instead of just V. And so it turns, and the matrix here is A dagger. So it turns out that if you set U equals to 1 over S times AV, the U's actually turn out to be eigenvectors of A dagger. This is going to get covered way more in a class that you're going to take, but I am going to show you an abbreviated version of how I use the SVD in imaging in my research in a moment. So right before we move on, because some of you are going to be taking optimization courses, I do want to cover the other cases of stationary points that you can have when you are optimizing an objective function. So you remember that if that second derivative matrix H was positive definite or positive semi-definite, it would give you, you know that you were at some kind of minimum point or dip in the function. So if H is positive definite, then F is called strictly convex at that point, and that gives you a single point minimum. If some of the eigenvalues are 0 and some are positive, then you get a minimum, but it might not be a unique one. So it might be part of like a contiguous set of minima, like a line. So this is like a half pipe. I don't know if any of you are skateboarders, but like the bottom of a half pipe is an example of a non-unique local minimum, because there are a bunch of points that are all at the minimum height, but they're all touching, and there are more than one. There is also a case called indefinite, which would be where H has at least one positive and one negative eigenvalue, and that's a saddle point. There are also, as you might imagine, analogous cases called negative semi-definite and negative definite, where instead of positive, you have all the eigenvalues negative or all non-positive, and those correspond to the hump cases, the hump versions, the flipped over versions of the local minima, and in this case, you have maxima. It is also possible, of course, to have functions where you have like where you have only 0 eigenvalues of H, and in those cases, you are probably going to have to use the third derivatives and the fourth derivatives to figure out what's going on there, and I'm not going to cover those cases. So just note that this slide doesn't have all the cases that you might encounter, but these are the most common ones that you will find like in optimization theory. Cool. Let's get back to image reconstruction, shall we? So now we have a way to solve our problem, except for the fact that we have this pesky noise term. The noise, our solution, like I said before, is going to be very sensitive to this noise because the columns are are almost linearly dependent. And so what we do instead of minimizing y minus ax squared is we add this small additional penalty on the size of the elements of x. So what this does is it basically says, okay, we want a solution that like matches our data, but we don't want the values of x to be like enormous. And we're gonna have this penalty term where we take a small number, lambda, times the size of x, so that solutions that have crazy high values of x, like it doesn't pick them. In this case, you can get a formula for the pseudo that looks a lot like the pseudo inverse that I described before, but there is, instead of A transpose A, you have A transpose here, and you have a lambda squared added to the thing inside this inverse. This matrix inside the inverse is always invertible when lambda isn't 0. And of course, lambda isn't ever going to be 0, because if it were, then you'd just be doing your old problem, because this term would go away. So in this case, you get a better behaved solution. And lambda here is called your regularization parameter, and that tells you the relative strengths of these terms. And basically, the higher you make lambda, the less you trust your data, and the more you trust the belief that you shouldn't be getting big values in your image. There's even a step further, which is that you need, in DOT, it turns out that the sensitivity profiles are so small at large depths as you go deeper into the brain that you actually have to apply a different level of regularization for each depth. That is accomplished by, instead of using just a lambda here, you also use a matrix L that scales your penalty term based on how deep the voxel is. And that's described, well, which is really based on the size of the columns of A. I do not want to dwell on this because it is not super important to understand the results that I'm going to show. But I do, for those of you who do DOT or want to do DOT, I do want you to see that this is an additional complication that you will need to think about. And this, again, I'm not going to go through this in detail, but this is the math showing what would happen if we did the setting the gradients equal to 0 and looking at the second derivatives to check if this is a local minimum. But we do it for the fancier case where we have this extra term here. And when you do that, what you find is that the gradient setting that equal to 0 gives you this fancier formula for the optimum solution. But here, the second derivative matrix, instead of being 2 times A transpose A, it's 2 times A transpose A plus this extra little bit of the identity matrix. And so if you, this matrix here is positive definite, not semi-definite. And so this matrix is invertible always. So, okay, connection to singular values and the regularization parameter. Now we can start to use all of this knowledge to understand why what I showed you about the imaging system is true, and maybe even how to make it better. So this is the formula for the solution X that we get when we do this minimization problem. And there is a relationship between this and the singular value decomposition. So going back to the singular value decomposition, I want to talk about what each of the parts mean. DOT sensitivity profiles are really diffuse. And so what that means is that you can kind of think of this A matrix as like a low pass filter. When you pass an image through your DOT system, it's basically taking that image and it's making it really blurry before it converts it into measurements Y, because it's not sensitive to super sharp edges in the image. And so if we think about what has to be happening on the right-hand side of this decomposition to reflect that property, what you can see is that the singular value decomposition is a lot like a transfer function if you've seen signals and systems, and if you haven't, then you will later this summer. So here, SII, which is the ith singular value of A, is the gain for, it's like how much this spatial pattern VI gets amplified when it goes through the A matrix. And so big values of S have to correspond to spatial patterns that are low in spatial frequency, that are really smooth. And so it turns out that we do see that when we look at the singular value spectrum of A. So here, what I've done is I've taken the SVD of A and I've plotted each S value, but I've arranged them so that they're in descending order. You can have, whenever you have a basis set, right, you don't have to put the vectors in any order, right? You can choose what order you have them in. It just matters that they're a basis for the space that you care about, right? And so I'm taking those V vectors and I'm just ordering them so that the S that they correspond to, the eigenvalue they correspond to, is descending. But if you arrange them this way and you look at the spatial patterns V that correspond to big singular values, which are over here, you can see that they are activity patterns that have giant blobs. And as you get to smaller singular values, those correspond to these spatially sharper or higher frequency activity patterns. So, okay, that might make sense to you, but like, why does that matter? And how can we use it for imaging? Well, it turns out that the formula for that pseudo inverse that I told you about is related to the singular value decomposition. So you can also write this formula in the following way, where if you take the vector y and you multiply it by this regularized pseudo inverse, it's going to get multiplied by this SII divided by SI squared plus lambda squared. The reason why this is significant is that the lambda here reduces the influence of cases where SII is small. So let's say that there was no lambda. So lambda equals 0. Then this fraction here is going to reduce. It's going to turn into 1 over SII squared. Because if lambda goes away, then you have S over S squared, which is just 1 over S. So when that term, that 1 over S, gets together with this noise E, when it multiplies E, if S is small, it's going to blow up the noise. And that means that you're going to get back in your reconstructed image huge contributions from these high spatial frequency patterns that you know don't get sent through your imaging system. So what lambda does is it basically dampens that effect. So it says if SII is small, then I am not going to multiply like anything by 1 over SII. I'm going to multiply it by this instead. And that means that it gets multiplied by a smaller number than it should be, which introduces a bias into the solution, but you don't blow up the noise E. In so doing, because you are essentially not compensating appropriately for the low sensitivity of these patterns, your solution is going to have in it more of this low spatial frequency content. So the higher lambda is, the more you are distrusting these high spatial frequency patterns. And that creates a trade-off between image resolution or sharpness and how sensitive it is to noise. So what you can do here is if you look at two imaging, so different imaging systems, right, correspond to different A matrices. So if you take the singular value spectrum of two A matrices, the singular value spectrum that dies off less quickly is going to allow you to set lambda. It's going to allow you to trust the information in these high spatial frequency patterns more than this fast decaying singular value spectrum. And so if you set lambda for this ultra high density system, which is in red, you should be able to set it lower for the red system than for the blue system before you start getting crappy images. So the reason why that's important is that you can see that the UHD, the ultra high density system, right, because it has a less quick decay, should give us a better noise versus resolution trade-off than the high density system. And it turns out that that's exactly what we see. So if we do that simulation I told you about before, where you put a fake target in the head and then you reconstruct it, but you use different grids, you can actually find that if you switch, like if you sweep the parameter lambda 1, so you progressively decrease it, what happens is your images get noisier. They also get higher in resolution, so the blob width down here decreases. But if you pick a given noise level, the ultra high density grid gives you a higher resolution image than the high density grid when it's at an equal noise level. The reason why this kind of curve is also important is that lambda is kind of an arbitrary like fudge factor. And so when you're showing that an imaging system is like better than another, you kind of want to show that it's better for like a wide range of lambda values and not just like the couple of lambdas that you might have cherry picked. And it makes it more robust that way. Okay, we went ahead. That was a positive result. We built the system. This is what the system looks like. We confirmed in vivo, we imaged people, and we got this kind of same pattern with noise versus resolution trade-off. At the beginning of this talk, I promised you that we were going to decode what kinds of movies people's brains were responding to. So I'm going to quickly tell you how we did that. We showed people 4 clips, and our goal was to figure out which one they were seeing. So if you were in our experiment, you watched a run, several of these runs were in random order. We showed you these different 90-second movie clips, and at the beginning, we showed you a 20-second movie clip. On either side, we also showed you a fixation cross to kind of prime your attention. And in each run, the order of clips 1 to 4 was random, the dummy clip was unique, and every session would include 4 to 8 of these runs. So some sessions were short or long, depending on how much endurance you had and how bored you got. The clips were all taken from the successful fMRI decoding study that came out of this lab. The clips did not include any audio, so we were decoding just based on visual information and visual activity. We used what we call a template-based decoding method here. So what we did is we split up our trials into the first half of the imaging session and the second half. For the first half, we called them training trials. And what we did is we took the brain's response to every clip and we block averaged those responses to form the mean response to every clip from the training trials, which are called templates. And then for the second half of the session, we took the trials, we took each trial and we took its correlation over space and time with each of these 4 templates. And we told the computer to guess that the clip that was viewed in any training trial was the clip whose template that trial's brain activity correlated the most with. So this is a maximum correlation classifier for those of you who know something about machine learning and classifiers. And we also threw out the first 20 seconds of each clip response because we didn't want bleed over from the last clip due to the fact that the blood takes some time to respond to the brain activity, which is like there's electrical activity that then gets translated to blood in a delayed manner. From this, you can calculate the accuracy of your decoder. This is just a matrix showing what was guessed in each trial. I don't want to dwell on this, but I do want to, because the focus of this talk isn't really the decoding, but the point here is that the accuracy of the decoder is the fraction of trials that it got right. So the number of things it got right divided by the total that you asked it to decode. And you can calculate the decoding accuracy for each of these 2 imaging grids in each of the imaging sessions. So here, each data point on the graph is an imaging session, and they're grouped by subject. So the results here are shown by 4 subjects for whom we got good data quality. And what you see here is the decoding accuracy is really pretty good. So chance level, if you just like threw a dice and had it pick a decoder or pick a clip randomly, right, the chance level would be 25% because there are 4 clips to pick from. And this is all of the versions of DOT are doing better in all the subjects, way better than 25%. But what you can see is that the blue dots are generally higher than the pink dots, and the pink triangles, sorry. And the pink triangles here are from the high density DOT, the version that's high density, where you ignore measurements that come from like super close sources and detectors. So this is just to quantify that. The average accuracy for the higher density system was 93.3%. From the high density system, it was 83.2%. We wanted to go a little bit further than this and say, okay, these are long clips, right? They were 90 seconds. Can we use less data? It turns out that if you take a clip and you just change the amount of data that you pay attention to, so you ignore the first 20 seconds, but then you change the amount that you pay attention to, which is D, the duration, then you get, as you would imagine, you get lower decoding accuracy if you're using less data to decode, but you can use pretty little data, like down to 10 or 5 seconds, and still get way higher than chance performance. And another way to look at this is that if you were designing a system and you wanted to get 70% accuracy out of it, if you draw a horizontal line here at 70, the higher density system requires about 50% the amount of data to get that accuracy than the lower density system, which is shown by the pink curve. So this was an encouraging result. This basically showed that ultra high density systems give us some benefit when we're trying to do a decoding task. Something that I will quickly go through because I know that we're running probably short on time and I want to leave some time for questions, is that you can do a fancier version of decoding. So what I just showed you, template-based decoding limits you to guessing what clips someone saw to the clips that were in your training set. But in most machine learning contexts, you want to be able to guess what people are seeing, and you want to allow your guesses to maybe be outside of your training set. And so in template-based decoding, because the predicted response to a clip is just that template, you can't guess clips outside of the training set. But if what instead you did is you were able to predict the brain's response to any clip using some kind of model of how each brain location responds to different parts of a movie, then you could start predicting the brain's responses to a whole collection of clips. And from that, you could predict which of a whole collection, not just the ones you trained on, were seen. So to do that, we use a linear encoding model, linear regression, linear algebra. So here, what we do is we take a movie and we break it down into these different features, which are called Gabor wavelet motion energy features. I'm not going to dwell on this pipeline, but basically what they're doing is they're telling you what's going on at a location in the movie at certain spatial frequencies, speeds, and locations. Basically, this is like how fast certain edges are moving and how sharp the edges are in the movie. And what you get is a time trace for each of the edges that you care about, which are really Gabor wavelets. You get like how much activity is happening, how much that type of edge is changing at a location in the movie at a given time. That is your movie feature regressor matrix X. And what you can do then is you break every movie down into its features X, and you measured a bunch of brain activity during that viewing, right? And so what you can do is you can calculate how sensitive every voxel is to fluctuations in each of those visual features. And because we're modeling that as a linear combination or a weighted sum, this is a linear regression problem. And that means that we are trying to solve for the weights B given knowledge of X and Y, which you can use a regularized pseudo inverse to do, just like in image reconstruction. But here the meaning is different. Here you're getting model weights B instead of voxel values. But it's the same math, and the foundation is all the stuff that you learned earlier in this talk and in the summer. And so what you can now do is for an unknown clip or a test clip, you can calculate its features X, but here, now that you know how sensitive each brain location is to those features, you can predict what the brain activity will look like in response to that clip. So what you can do now is a modified version of the decoding task where you take a test clip, you calculate the predicted response that the brain is going to have to that test clip, and then in your test trial, you calculate the correlation between the brain activity that you actually saw and the brain activity that you would have seen for each of these clips, that you should have seen for each of these clips. And you tell your decoder to guess that the clip that the person was seeing was the clip whose predicted response is most correlated with the actual response that you got in that trial. You might notice that I have this funny word called lure clip here, which is that because this study had 4 clips, you have to use at least 2 of them for training. Actually, you can use 1 for training, but that's a little bit too little data. So since we're using clips 1 and 2 in this case for training, 3 and 4 are for testing, I actually throw some clips that the subject haven't seen, so clips 5 and 6, into the decoder so that it's still guessing between 4 things. So chance level is still 25%. That's the reason you see clips 5 and 6 here. But the accuracy is the same. It's the number it got right over the number total. And when you do that, you can also do this for training clips being not just 1 and 2, but 1 and 3, 1 and 4, 2 and 3. In machine learning, you can always split your data different ways, right? What you call the training and the testing set can vary. And you should vary it to see how sensitive your result is to just different splits of your data. When you do that, these are the decoding performances that you get for each session. So you get 66.7% average over sessions and training clip combinations or splits. That is statistically significantly higher than the chance level within each subject. We would love for this to be higher, but if you want to guess what movie somebody is seeing out of a totally unknown sample or unshown sample of movies, your training set has to be big. This training set was only a couple of clips, only a few, right? So if you did this real problem where your goal was to do this out of sample decoding, you need a much bigger and more diverse training set, right? You all have probably heard that in machine learning and AI, there are huge problems when you train on data sets that like don't have any people of color in them. You end up with like racist decoders, right? And it turns out that like if you don't have a representative sample, you're going to do a poor job of getting an accurate result when you go out of that sample. So here we chose our experiment because our initial goal was this easier decoding task, not out of sample decoding. So the fact that we got decoding accuracy that was this high on an experiment and a sample that wasn't super diverse of movies is actually kind of encouraging and surprising. I was frankly expecting this to go down to 30%. So it's not as high as you would want, like for Siri, but it is a lot higher than it should have been, given how bad of a data set that we threw into it for this kind of task. By the way, the reason we didn't use a very diverse set of movies is because we couldn't take a bunch of movie footage data because COVID happened around the time that we finished the first data set collection. This is how we salvaged the data from my thesis project from having to be delayed for 3 years instead of 1 year from COVID. Great. If you increase the number of fake clips and you ask the decoder to decode, it turns out that everything stays above chance when you do that. I'm not going to dwell on this result. This is just basically things stay above chance when you ask it to go between a bunch of clips instead of just 4. And the punchline of this, all of this, is that HDDOT is indeed a modality that has a lot of promise for doing more complicated decoding tasks, but because it's more portable and lighter weight, it might be that we can now do more advanced decoding in people who are super, super paralyzed and give them more options than just yes or no to talk to the loved people in their lives. Future work is going to extend this to a greater variety of stimulus types and harder decoding tasks, and hopefully take a lot bigger data sets now that we know how to handle COVID and we're not just all out of lab in quarantine. And with that, I would like to give a lot of acknowledgements to the wonderful collaborators in this project and to provide a list of references cited. And with that, I will take questions.
Yeah, thank you so much for that talk, Zach. That was
thank you.
awesome.
Very cool
so
stuff.
we have a question actually straight out in the chat, so we can quickly go for that one.
Yeah, Shichin, that
yeah,
is. Oh, go ahead. Sorry, what did you say?
I was gonna say, if you want to read out the question and then go ahead with your answer.
Yeah, that's a great. So I'm glad that you reminded me to read the questions. I don't know if I was doing that before. So Shichin has this awesome question, which is, how do you detect which part of the target light comes from which source light? Do you light them up one by one? That is a fabulous question that we actually spend a lot of time designing in our lab. So I'm going to go quickly back to the DOT system to show you. So the answer is yes, that's part of what we do. So what we do to distinguish what light comes from what detector, or sorry, what light comes from what source, is we do turn on the sources one by one, but remember that I told you that we do use different colors, right? We use 2 colors. So if we really wanted to do everything like one measurement at one like time point, what we would have to do, or one light level at one time point, right? We would have to go through all of the sources again at the next color, right? But it turns out that we don't have to do that. So we actually use a strategy where we actually wiggle, we modulate the light level in the sources at the 2 different colors at different frequencies in time. So it might be that the light that has the longer wavelength, right, we wiggle that light at a higher frequency than we wiggle the other color. And so what we can do is that then, right, we get a time trace of light levels out that we then like Fourier transform, right? And then just like how radio decoding or amplitude modulation works in radio, right? We can then separate out which color was which by looking at the fluctuation frequency. Those fluctuation frequencies are much faster than the brain related fluctuation frequencies. So we wiggle the sources light levels at frequencies in the kilohertz range, but we don't, like the blood goes way slower. So that's how we can separate out like the wiggles that are due to, like that we're using to discriminate the colors. Like we can separate those types of wiggles from the wiggles that have to do with the biology. Does that make sense?
I'm just going to comment real quick. That's very cool. And I didn't know that DOT encoded and decoded in such direct analogy to MRI.
Yes, it's, you know, we are, unfortunately, we are less, our forward model is less well conditioned than a Fourier matrix.
Sure.
But you're absolutely right. It's like you're basically programming like your light to wiggle or sing at a different frequency. And like, that's like you said, exactly like an MRI, a huge portion of the spatial encoding is that you make different slices precess at different frequencies. And that's how you can tell like which slice things are coming from. So this frequency encoding is used across a lot of imaging science and imaging systems. And one thing that I do want to point out is that, so the strategy where you turn on each source at a time within a color is also called time domain. We call it time domain encoding, or also called time domain multiplexing. And so what it means is that for every time point that you want to look at the blood, you actually have to cycle through the sources each once. And so the amount of time that the detectors and the sources are reporting or on is actually a lot less than like 1 second or a tenth of a second, which is the amount of time like over which when they all cycle through, they get one measurement. Kind of like how an MRI, to get a volume measurement, you're actually not imaging every slice at the same time. You're imaging each slice like in rapid succession, and then that whole volume gets treated as one time point in the blood's eyes.
So I have a question about that. I don't want to, if other people have other questions, I don't want to.
I guess.
Oh yeah, we should go to Senscar's question.
Okay, I'll go to Sen's question first, but don't be shy, Ty, because I want to make sure I'm answering stuff.
Well, other people.
Yeah, I think Ty was a good follow-up, and yeah, after Senscar's question, we should definitely follow up with your.
So Senscar says, can this work on people in, for example, coma, to be used either to know what they are thinking? So that is an awesome philosophical question that is being addressed in the MRI community. There are people who will use this, who have tried to use these kinds of methods to do like dream decoding. And with dream decoding, it's very, very difficult to know, like to validate that you are getting the right answer, because you can't like force someone to dream about something in a controlled manner where you can evaluate the accuracy of your decoding. So if someone has a coma or so coma is an interesting case, because coma is a situation where like they're unconscious. And so like they might not be like consciously trying to tell you yes or no. You might like have someone in a different, like, so by a locked in state, what I would mean in this talk would more be like somebody who can't move anything, but they are conscious, right? So they're like, when they want to say yes, no, or I'm in pain, they might be able to consciously like imagine doing math. Well, again, you can't see their output. So how do you validate that kind of decoder? Well, the answer is that if you ask them yes or no questions where you know and they know what the answer is, like, for example, is your like husband named John, right? Unless they have like they're cognitively impaired in a way that like they don't know the answer, or like what color is this, or is the sky blue, right? They're like, because everyone knows what the answer should be, you can validate that. Whereas like you can use this method to reconstruct or to, you can extend this to decode or reconstruct like estimates of what someone might be dreaming about. But like there's always going to be a huge, and rightly so, dispute about like, well, were you really decoding what they are dreaming? And that's a big, from an ethics point of view, that's really critical, because like obviously if you could reliably trust what, like you could decode what someone's dreaming about, then that's a way bigger like ethical concern than if you can only decode like what someone chooses to think about and chooses to tell you, like not just what they choose to think about, but what they choose to tell you, like what they imagine revealing to you, what they imagine saying to you, yes, no, as opposed to like the background thought process that they're going through to determine the answer yes or no before they try to speak it by doing mental math, if that makes sense. The other reason why I think that even though there are, as always with any technology, there are ethical concerns, why this technology I think is maybe less ethically concerning than Elon Musk's Neuralink or an implant one, right? Is that if you have an implant, you can't just rip it out. If you're not happy with you or someone else recording from your brain and you have a wearable device, you can just take off the device, right? So we're using a wearable system, ironically, but importantly, also like helps to address some of the potential ethical concerns, at least in my sort of naive thinking about this technology. If you're really interested in the ethics behind this, you could, there's a woman named Anna Wexler, and there's a guy named, I believe, Raphael Yuste, who does a lot of thinking about neuroethics and how that relates to technologies ranging from brain-computer interface to just like what your Apple Watch can measure, which isn't really a brain-computer interface, that's more of like a pulse computer interface. Those are all really interesting questions that are beyond my area of expertise and pay grade, but nonetheless, like, you know, we don't do science in a vacuum, and I personally like the fact that you have more say in whether or not you can, you know, take off an imaging system like this if you're really concerned that somebody is gaining access to unconscious processes. But for now, we are very, very confident that they are only gaining access to conscious processes. And I mean, right now we can't even decode, we can decode 4 things, right? But like, if you're trying to decode like fleeting thoughts, right? I mean, there's no way that we've got that capability. And so I would be very skeptical about anybody who would make claims about being able to decode unconscious content or unintentional content. Does that make sense?
Zach, I just want to say also, great talk.
Thank you.
This was awesome. Thank you for going through so much linear algebra content. Thanks for teaching singular value decomposition. It's very nice, very helpful.
Yeah, I was going to tell them about how to project onto a column space, but I decided that would be, you know, that would be too many lectures. So you all will learn about SVD in more detail in your courses. But you're welcome. And some of the stuff I covered was also covered in the optional modules. And so really you should go read David, if you're interested in these things, you should go read David Lay's textbook chapters on them, like least squares, you know, solutions and whatnot.
It's a good book. I ended up liking it a lot more than I thought I would when I first started it. But I wanted to ask a little bit more about conditioning, and in particular, right? So we talk about the very undetermined nature of any image reconstruction problem, which, by the way, will be a central focus of your thinking during the mathematics of imaging science class. To put it mildly. So I was wondering, you were talking about this sort of, you know, the color modulation that the per color modulation that you guys do, the frequency modulation. And so my first work was in undersampling reconstruction in MRI, right? Okay. Trying to get accelerated scans. So I was just wondering, is time resolution often a concern here? Or do people do a lot of time domain undersampling or other types of like, essentially like clever regularizations that make use of some of the non-uniformities in, say, your sensitivity functions, right? Where you fill in gaps based on these point spreads, that kind of stuff. Does that tend to be like a feature of the literature, or does it come up less often?
Oh, no, I'm really glad you brought this up. It comes up all over the place. Like there are people, in fact, I'm going to head over to that, to the inverse problem slide. So like this slide is usually about as complex as our lab goes with the reconstruction, for reasons that I'll talk about in a second. But when we, for the students, for the new folks, this penalty term is one that like we chose arbitrarily, like to make the images not blow up at certain places. But like Ty is alluding to, there are people who, for example, will penalize on the gradient of the image, right? Which is called a total variation penalty. And so there you're looking for images that don't have sharp edges, but you don't really care about like how intense they are at certain spots. And so in DOT, people have tried all sorts of different regularizers. Like they've tried not, instead of using the 2 norm, they've used the 1 norm, which is a way to sparsify your image. And in terms of undersampling, time undersampling, I wouldn't say, so the reconstructions that I talked about today are all 3D reconstructions that we do at individual time points. So they aren't genuinely 4-dimensional, so they don't like use the blurring in time. They just use the fact, like they use info about the spatial blurring. But there are people who do DOT image reconstruction on time traces, like where it's a 4-dimensional reconstruction, where instead of Y and X being like measurement set and image at a time point, they're like a whole movie. And then you're solving for the whole movie at a time. And those situations, usually temporal undersampling is not an issue there, because the blood, the hemodynamic response to, like the brain works, the brain's language is electricity, right? So the signals that have biological meaning, right, are like neurons firing things electrically at each other. And that happens way faster than the blood's response to the neurons in that area. So like we image, like our imaging systems will go through like one full cycle of our sources in like a 14th of a second. Like, so our frame rate, like from one of these systems, is typically around 10 to 14 hertz. And there's a trick that we use called 2-pass, where we do bright and dim, because it's the short distances get saturated, and so we use a bright pass and a dim pass to like improve the dynamic range, but that's kind of beyond this. But if you do that, you lose a factor of 2. So the point is that we're at least 7 hertz frame rate. And so 7 hertz is like way faster than any of the biologically meaningful like blood dynamics.
Right.
Or at least
the time scale just kind of averages everything away.
Right. And so what ends up happening, like, for example, like cardiac pulse, right? Like your heart beats, like assuming that you don't have a malfunction, your heart is going to beat somewhere around like 0.5 hertz to 2 hertz.
Right.
Like 1 to 2 times a second. And so we can see that in our signals. And in fact, we see like our system is like pulse is huge. And the brain related components are actually a lot weaker than cardiac pulse. But cardiac pulse is such a tight frequency band around 1 hertz that you can just low pass filter the signals to keep the brain related part. But so actually we use that as a data quality metric. So when I talked about like, you remember how I said, hey, we imaged these 4 people, I reported results on these 4 people who had good data quality. Well, we also imaged a couple more that didn't have good data quality. And the reason, one of the assessment of data quality is if you can see the cardiac pulse, because DOT systems are kind of like microphones that image both a whispering mom and a screaming baby. The pulse is the screaming baby. The mom is whispering, or talking softly, but at a different frequency. So if your imaging system couldn't even hear the screaming child, then that's a bad part. Then you have like a problem, right? Like you have a bad source or detector. So what we'll do is we'll actually split out our signals into like the pulse band and the not pulse band. And the pulse band we will use for data quality assessment, because it's usually true that whoever we're imaging has a pulse. If they don't, they are not being imaged in a DOT system. They are probably being imaged or not imaged and have a defibrillator hooked up to them.
Mm.
It turns out that people who don't have pulses tend to be in medical distress. So, you know, we use the detective. We use the, yeah, I know, right? Controversial, right? Very controversial. Yeah, fortunately, we have never had to call a code in a DOT scanner, but like if someone's heart stopped beating in a DOT scanner, we would of course immediately pull them out. And, you know, we would call protective services, like, right, there are protocols for getting people the heck out of the scanner, right? But anyway, the point is that like the pulse is like part of data quality assessment. And that's also part of why like we can even make a judgment about image quality that doesn't relate to like the hypothesis we're trying to solve or trying to show or not show, right? Because like you can't just have a subject that decodes badly and just say like, oh, well, this is a bad, like that's huge confirmation bias, right? Like you have to be able to have a measure of image quality that is different in some way from like the kind of like hypothesis you're testing with the imaging system, unless your job is to just check that the imaging system works. And so for that reason, like, because we are always, but anyway, to get back to your original question, like, because we're always interested in components of signals that are way slower than like the imaging system's frame rate, like we have the ability, if we wanted to like massively undersample in 4D. So you might say, well, hey, why don't you do 4D image reconstruction, right? Why don't you just include in your regularization term, right, like an operator that basically says that if you get a 7 Hertz signal, it's probably wrong. And the reason is that we often have to use direct inversion. It turns out that our A matrices are so ill-conditioned that if you try to use iterative methods to reconstruct them, like, or reconstruct images like gradient descent, your steps will get so small so fast that you will not converge to a good solution. And again, this is, I mean, this function, even just this function, if you do Landweber descent on this, gradient descent, Landweber iteration on this objective function, this is a strictly convex objective function.
I should say.
But it is so darn slow to converge. And no, I kid you not. There's a graduate student in Mark Anastasio's lab whom I work with, and they're working on a neural network based reconstruction of DOT images where the structure of the network is actually inspired to some extent by Landweber math. Okay. And so they're the ones who made a lot of the innovation, so I don't want to reveal too much about their stuff without their permission, but basically they thought, okay, well, if we're going to use a neural network to do this, we should probably just double check that Landweber itself is good, or at least works. So they said, Zach, this is a strictly convex objective function, and we're going to try to use Landweber on this because there is no reason why Landweber shouldn't work. And I smiled and said, I agree with you. Joe says it doesn't work. Joe says he's tried this and says that he has to use direct inversion, which involves inverting a 30 gigabyte matrix, for which we have a server, by the way, that has about a terabyte of RAM.
Yeah.
And you can do it on a server with 256 gigs of RAM. But, why? I mean, Joe is like, go big or go home, right? If he's got the money, just buy he has a server that has 1.5 terabytes of RAM. He said, spec out a server with as much RAM as you can give me. So I did it. And he was like, all right, happy Christmas. And, we got this. So anyway, we don't need that much RAM, but we need a lot of RAM to do this. But it turns out, so Mark's student went and did the Landweber iteration, and it had not converged after, I think, 2 weeks.
This is very flat near the minima.
Super flat near the
minima. Or maybe all over the place.
I know, right? And so, interesting. And it just, the other thing about and I think he tried different like ways of setting the step size, and he tried like setting it like in a way that was inspired like in a provable way based on I think the Lipschitz constant and the norm of the matrix, and it was just, I mean, it was just excruciating for him to watch this poor thing not convert, and that was one frame, right? When you do iterative methods, one of the chief disadvantages of them, unless you're doing a 4-dimensional reconstruction where you're getting the whole movie at once, if you go frame by frame, you have to do that descent. You have to do the iteration once per frame. And so in our case, even though it is computationally expensive from both a CPU and a memory point of view to calculate this giant regularized pseudo-inverse, it turns out that because once you get it, you can just multiply this thing by all of your data vectors. And then you get everything in one shot. And on these, as long as you don't run out of RAM, the limiting factor in that, the computationally limiting step in that is calculating this inverse right here. And this inverse is usually the way MATLAB will do this is technically it'll pick the algorithm based on what type of matrix this is. Frankly, since this is a positive definite matrix, I'm kind of surprised that MATLAB doesn't use Cholesky, but I think it uses QR. I'm like 90% sure that it uses QR decomposition to do this.
That makes sense.
But so MATLAB will go do its QR, and that's really the rate limiting step. And then of course the memory limiting step is the amount of like side memory that it uses to do that decomposition. And then of course you have 2 copies of a 30 gigabyte or 10 gigabyte matrix flying around, which also take up plenty of space. But the point is, once you've got these big honking matrices, you just multiply, then it's just matrix vector multiplication, and you get all your stuff in one shot. And I think that stage of processing on one of our servers takes about, for a typical run, I want to say that it takes around 10 minutes, which certainly beats a week not being quite converged.
Right. Well, I have a lot of follow-up questions, and would love to talk with you about this at length, but I think we should probably call it. Unless, pausing for a moment for anybody to toss in any final questions. Okay, yeah, I think we're good. But Zach, thank you so much for coming and talking to us, sharing your work, tying it into the course. Really appreciate it. Really appreciate having you.
Thank you so much for the invitation. I do enjoy teaching. It's one of the things that I do miss a little bit about being in a stage of PhD and in a program where there is just less teaching. Thank you for the opportunity. And also it's great to meet some of the incoming students whom I'm sure that I will see around social events and maybe even lab rotations, depending on if the Adams or Joe have open projects, which I actually don't know if they do. If you want rotations with them, you should ask them. But the point is, I'll see you around. If you like this talk, great. If you didn't, then hopefully you'll be able to escape me and my loud voice at these social functions. I will do my best to make sure that whatever outcome you will find favorable is in your hands. And don't hesitate to email me if you have any questions about this or about like anything about the program or labs that I can help with.
All right.
Thank you so much, Jack. That was awesome. Great presentation and really great follow-up. And hopefully we'll see them. We'll try to do our best to convince them to join the BRC. So
yeah. Oh, I see a new. Oh, you're welcome, Jichin.
Awesome. I don't know if you need to pause the recording before we end the call. I don't know.
We don't. It'll automatically stop.
Okay.
Yeah.
Awesome. All right then. Well, thank you guys for coming. Thank you everyone.
Yeah. Helping us close out the course the right way. We'll see you all next week for Signals and Systems, we hope.
Awesome. Oh yeah, and after that, if anybody wants it, I can prove to you that the SVD is actually a generalization of the Fourier transform. But I don't want to do that before you know Signals and Systems. So.
Well, Zach, what's not a generalization of the Fourier transform?
Yeah, I know, right? Yeah, it's like at that point you might as well just be like Fourier is basically like Fourier's. I don't know. It would be, I guess it's kind of awkward if I called. But yeah. Anyway.
Anyway, I want to talk to you about low rank decomposition sometime soon. But
yeah. Great.
Anyways, thank Thanks for coming. Thanks everybody for coming. Goodbye.
Bye.